I kind of want it. Wow. Okay. So he has no excuse for coming in late. Wow. Okay. That's amazing. No, because I can always check the addresses with Sylvia, so you didn't rat him out. Ratting him out would be like saying, oh yeah, he told me yesterday he's not going to your class because he says you are a blank. Oh, what did you do? Here, hang on. Anyway, there we go. Okay. So what we're going to have a look at now something called logarithms, or just logs for short. Okay, all right. Are we looking yet? Okay, so last time we were looking at powers. So suppose I want to answer a question like this: 2 to what power equals 8? So we know it's 3, yeah. The way we write this as a calculation is like this. We write log 2 8. And that literally means what power do we need on the 2 to make it an 8? It's exactly what it means. So here the answer is a 3. What power would you need on a 10 to make it a 100? 2. Yes. That is okay. And then we'll do one more as an example. What power would you need on a 5 to make it a 125? 3. Wakey. 9 o'clock is difficult for you, yeah? Okay, we get the idea here? Yeah. So, the way we label these, that you need 2 parts, well, 3 parts I suppose. So does anyone know what this number here is called? Its name? Anyone know? No? Okay, this part is called the base. And this part is called the argument. And this one here really is the value or the answer. Okay. Just like with powers, there are rules here for logs. Let's have a look at them. Can I go down? Yeah? Okay. So actually, before we start, we usually deal with the base being a positive number. Okay. And we don't usually think about the base as being 1, because that doesn't really make sense. If I wrote like log 1 9, that doesn't have an answer, because 1 to what power makes 9? Well, nothing works here. So usually the base is bigger than 0, and we don't consider 1. There's nothing really wrong with the base being less than 0, because, it could be negative. It's not a problem. But we usually deal with it being positive. Usually, but it's not a problem if it's negative. Okay. Right, so the first rule, rule 1, log base b of x multiplied by y is log base b of x plus log base b of y. So you could check that out with numbers. So if you had log base 2 16, for example. 16 is 4 multiplied by 4, isn't it? So you can see here this is log base 2 4 plus log base 2 4. 2 to what power makes 16? 4. So this is 4. This is 2. And this is 2. So you can see that it is true. Okay.
I think you can take 2 in the front as well.
Yeah, there are many rules. Yeah, yeah. So you're right. You're right. Yeah. This is the most important rule. Why is that? Why is this so important? It's the most important rule for logs. In fact, it's the reason logs are important. What is so important about this?
Where you can divide by x and y.
Not this. Who's this going to be?
Anyway.
Ah, no, Shumway. Why on earth are you so late? No, hang on. Don't you live on this floor?
No, that was Leon.
Oh, that's Leon. Okay. Wait. I think from this point on, I'm not going to let people in my class after 15 minutes. So it's a little bit too late for you. Okay. Now, if you want to stay, that's fine, but I won't give you attendance. So it's your call. Stay or go. All right, fine. So yeah, 9 o'clock is starting to become a bit of a problem for some people. So if you're more than 15 minutes late, I won't give you attendance, and I might not let you in if it continues to be a problem. I think it was a problem last week as well, wasn't it? Wasn't it? Are you sure? I could have sworn you were late last week as well. Maybe I'm mistaken. We'll count this as the first time. Yeah, even though I think we all know it's not. Okay, so why is this rule so important? No one knows? No? No? No one wants to guess? No? The reason it's so important is because here is a multiply and here is a plus. So what this is letting you do is go from a multiply to a plus. Which is easier to do? Plus. So anyways, it's not important nowadays, but in the past, logs were used to simplify difficult multiplications. Okay. Anyways, that's not such an important reason right now. So let's look at the proof here. So the proof is let x equal b to some power and let y equal b to some power. So then you have log bxy equals log bxn xm, which equals log bxn plus m. This is the first rule of powers yesterday. Oh, sorry, what did I write x here? I'm sorry, no, this should be b's here, sorry. These are b's. Log b power n plus m. So what does this equal here? From here to here, what can I get? Yeah, it must be n plus m. It makes sense. B to what power makes b power n plus m? Must be n plus m. But I could write this as log bx, because b to what power makes x? Well, you can see it here. B to the power of n makes x. And what about m? Sorry, m. That's log by. B to what power makes y? M. So this is the same as m. And in fact, that's where you wanted to finish. So this is the end of the proof.
Can you repeat it again?
No. Sorry. The only reason I say no is because I have 5 more proofs to go through and they're more difficult. But I'll upload the video later today. You can watch it again. You subscribe to my channel?
Yeah.
Okay. So you'll get a notice when the video's been uploaded, okay? The next proof is very similar to this proof. So similar, I barely have to change it. Log bx over y equals, I'm sure somebody knows this one, or could even guess. Yeah, log bx minus log by. Now the proof is so similar, I'll just use a different colour on the first proof. So I'll just change the first proof with green. So if I have log x divided by y, I want to show that it's a minus. I do the same thing. Log x divided by y, that's, sorry, there's another b here. Sorry. That's log bn divided by bm. But when you divide, what do you do to the powers? You minus them. So here is a minus and here is a minus. So the proof almost the same. It's not even worth rewriting. Okay, so that's the second rule. So C number 1. Okay, 3. Can I go down a little bit? Yeah. So we'll do, which rule will we do next? I think we'll do this rule next. B x power n. Does anyone know what this one is? Yeah. That's it. The n can be brought down into the front. And the proof? I think we'll use the first rule again. So this can be written like this. X, X, X. Da, 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 da. How many x's do I have? N. Now, I can use the first rule to change all of these into pluses. Log bx plus log bx plus etc. etc. Log bx. And how many of these do I have? N of them. So this is n log bx. So it's the end of proof 3. Okay, got that one? Yep. Which one will I do next? Maybe I'll do the change of base one. Or maybe the swap one. I'll do the swap one. Right, so log xy. If you ever need to swap xy, it can be written like this. 1 over log, does anyone know? Yx. So this is a handy, easy way to swap the base and the argument. If you ever need to make a swap between them, like this. Yep. I think, and the proof I will do, yeah, I think I'll do rule number 5, and then I'll use the proof from number 5 to prove number 4. I think this will be the easiest thing to do. So I'll leave a little bit of a space for rule 5, or if you want, no, we'll keep the order the same. No, it's just because in previous years, if you watch older videos, I do this is rule 4, but I think maybe rule 5 is a little easier to do next. It doesn't matter. So I'll leave a bit of a space. I'll prove 5 next. Okay, so we'll come back to 4 in a moment. So log base bx, if I want to change the base to a completely different number, so if I want to change the base to base a, for example, the price I pay for doing this change from b to a is I divide by log of the old base. So the way I always think about it is, from changing b to a, this is the price that is paid for doing that. That you have to divide your answer by log ab. Yeah? Okay, so let's have a look at the proof if I remember. Log bx. So I think what I'll do is I'll say let b equal an and x equal am. I think I'll do that first. So this would be log an AM. Yeah? I just replaced the B and the X. Now maybe somebody can see what this is. Maybe. A to the power of n, to what power makes A to the power of m? So if I write it here, A power n, to what power will make A power m? M over n. Because if you think about putting m over n here, the n's cancel, and you're left with m, which is what you want. So this is m over n. Yeah. But on the top, m. Well, that is the same thing as log base. What base? If I want something for m here at the top, if you look here, what could I say on the top? I could say it's log a x, because a to the power of m makes x. And on the bottom, log, I want n now on the bottom, so that would be log ab, which ends this proof now. Yeah? Yeah? It's okay? Yeah? Okay, we can go back to 4 now. So I could use proof 5 on proof 4, because I'm changing the base. I'm going from base x to base, what's the new base? Y. So if you want to use rule 5 to prove this, you change it to the new base. So what's the new base? Y. Y. And then you divide by log of the old base. But what's log y? It's 1. So you can see that proof, by using 5, you can easily get 4. Yeah? Can I just remove 4? Yeah, that's just one way to prove it. I think there is another way to prove it. You can do it a similar way to 5, I think. If I go back a little bit here, you could do the same trick as with most of the proofs. You could say, let x equal bn and let y equal bm. So then log xy becomes log bn bm, and what will this become? This will be m over n, yeah? Which is the same thing as 1 over n over m. And then what we can do, 1 over n is, where's n? This one here, so it'd be log bx, isn't it?
Yes.
And then down below here is log m is by. Now remember, b was a number of your choice. It's any number you want. So you could say, well, let b equal y, because it can be any number you want. So down here, if b is y, then you get log y. What's that? 1, and then this becomes log yx. But this is a messier proof. It's much easier to use proof 5 to prove number 4. So whichever you prefer, it doesn't matter. You don't need to write this one down. The other one was just fine. Okay, now last one, not really a rule, but just some values to consider. So log b1. So it doesn't really matter what the base is, you should know what the answer is here. B to what power will make 1? 0. Yeah. Also,
One.
what do you think? In fact, no answer here. B, there's no power you can put on the B to make this 0. Okay, so like for example, if you had log 9, 0, there's no power you can put on the 9 to make 0. Although I suppose if you really wanted a value, it kind of goes like this, negative infinity. So you shouldn't really have log of 0, and in fact, if the b is a positive number, which we said it usually is, here we use only the positive. So we can't really do something like 9 minus 1, because there's no power you can put on the 9 to make it minus 1. So we usually just stick to log of positive numbers. Okay. Now you might be thinking, well, if I have a negative base, then I could have a negative here. Which is true, but like I said, we usually keep the base positive. Okay. So we'll have a look at some examples. There are other rules of logs as well. It depends on what book you're using, you know, how many rules you want to learn. There is a rule, I can't remember. Some of the students asked me if they can use this rule. Yeah, it's like if there's a power on the base. Something like this. Has anyone seen this rule? No? Alright then, I'm not going to show you. So I'm just trying to stick to the rules that would be in the book and in the exam. So there are other rules. I give you 5 rules, some books give you 6 or 7 rules, and some books give 2 or 3 rules, okay? So we stick to 5 rules plus this kind of 6th rule. It's not really a rule, you just have to remember some important values. Let's have a look at some examples now. Can I scroll down? Yeah. Oh, actually, I should say a little bit about your calculator first, but we'll do that later. Okay, so the first example, we're going to try and not use a calculator here. So if I said log 16/256. So if you remember the last class, you should know the answer here. Nobody remembers this from yesterday? 2. Because remember I said 16 squared is 256. 2. What about this one? Log 25 625. 2. That's a bit better. 25 squared makes 625. And here's one. Log 10 a million. 6. Because 10 power 6 makes a million. Yep. There's some basic examples. Your calculator has a log function on it. We'll get to that later, okay? Yep. Yep, continue? Yep. Okay. Next now. For this question, I don't know. We want to simplify something like this. We want to simplify. Now we can't use the calculator here because there's an X in it. So we have to use our rules. So what rule could we use first, or what should maybe we change first?
The base.
The base could be changed first, yeah, or anything else? Huh, yeah? Change the second one, yeah. I think that's what we should do first. So which rule should we use? The fourth rule, which says this will become log x5. So if you swap the base and the argument, you turn the log upside down. Now, what to do next? Yeah, we should say that 35 is 7, well, no, sorry. Because we're adding, we can multiply the 35 and the 5. So that's 35 times 5. 175. Log x 175. Although I can make this a little bit easier, I think, because 35 is 7 times 5 times 5. Well, I don't think that's easier. No, I think log x 135 is as good as it will get. 175. Now, so what I was thinking was sometimes what you end up with is like a square number, for example. So if you had like a square number, you could change this into 3 squared, and then the 2 could come down. But that doesn't happen here.
We can get log x7 and
Yeah, and you can split it. Yeah, you can split it like this. So like if you wanted to continue, you could do something like log x 7 times 25 is the same thing. Which would be log x7 plus log x 25. But what's 25? 5 squared, yeah. It's log x 5 squared, and the 2 comes down in front. So you have log x 7 plus 2 log x 5. So these numbers are smaller than the original, but I wouldn't really say it's simpler. What's for the exam? The exams don't usually have questions like this. It's the next example I do, which is more like an exam question. So it's fine if you wanted to stop here, I would think. Yeah. Okay, we got this? I can go down? Yeah. Let me see. We'll do something like this one. Log 2 log 5 125 plus 6 log 125 25 minus 3 log 5 25. Yeah. Yes? Okay, so true, we can use our calculator, but in the exam they want to see the steps to simplify it. And again, just like yesterday, there are many ways to go to the answer. It depends which order you use the rules. So when I look at this, I have an idea of what I would like to do first. What do people think, looking at this?
125 is
Yeah, the base, maybe you want to deal with the base first, or yes?
no, don't deal with the base.
Yep.
125 is 5
To power, yes, yeah, yeah.
And take 3 into the front, so it will
Etc.,
six.
etc. Yeah, yeah.
And minus 3.
That's it, yeah. I mean, you have, the way I see it is you have two choices to start. You can deal with the bases first, or you can deal with these 1, 2, 5s, which are all 5, what do we say, 5 cubed, 5 power 3. And what's 25? 5 squared.
Square, yeah.
Now, what's wrong, Albert? No. Just be careful though, we cannot use the first or second rule yet. Why not? Why can't we use the first or second rule? Base is one problem, but what about the first and the third? Why can't I? The 2 and the 3. We can't do anything while the 2 and the 3 is there either. So we can't divide here. I think I'll deal with the base first and then the 1, 2, 5. Although it doesn't matter the order. You can deal with the 1, 2, 5 first if you want. But I just feel like it's this morning, this way. Log 5, 1, 2, 5. I'll do a swap here. That's 6 over log... No. I changed my mind. No, I want to think what's the best way to do it.
You can get the same, like, log 5, 5.
Yeah, I'll do what I was going to do. Log 1, 2, 5 here. I will swap these. Now, my advice here, these questions are usually a little easier when the base is smaller than the argument. So that's why I swapped them. Now, let's change the base here. So we can make them all the same base. Or I suppose I could put in the number here actually. What is log? No. We won't do it that way because we'll try and group everything together. So this would be log 5. Well, actually, then this is a complete waste of time swapping this. Doesn't matter. Log 5, 1, 2, 5, and then here is log 5, 25. That's rule number 5.
I think the first term cancels the last term.
Oh yeah, I can put the first with the last one as well, which I'll do in a moment. Yeah. It doesn't completely cancel, but you can put them together. Yeah. Right, so here we get 2 log 5, 1, 2, 5, plus 6 log 5, 25, over log 5, 1, 2, 5, minus 3 log 5, 1, 2, 5. And as you said, you can put the first one, you have 2 logs here, and here you have 3 logs here, so we can just minus them. 6 log 5, 25 over log 5, 1, 2, 5. And what do I get here? Minus, yeah. Log 5, 25. Okay. What is log 5, 1, 2, 5? Yeah, what's this value here? 3. So here we can get 6 over 3 log 5, 25 minus log 5, 25. Yeah, which part? No, you can ask me. No, don't be shy. I'm not that scary, am I? No, okay, alright, no, I won't force you to ask me. Okay, so 6 over 3, 2. And again, you have 2 of these minus 1 of these. Oh, then where's my mistake?
Yeah.
When you divide
So,
them,
this one is 125 and that is 25. You can't.
125. Oh my goodness, I wrote it down wrong, did I?
Yeah.
No. Wait. Wait, slow down, slow down. 1, 2, 3. Where was the mistake? Which line? 3. Oh my goodness. No, no, I see it. I see it. I see it, I see it, I see it. You should have said something sooner. I can't put... Sorry, my eyes read this as a 125. Yes. So you're all just sitting there going, let's see where he goes with this. Yes, I can't put them together. I can't. Alright, so we need to do something different then. No problem. Well, I can still change this here into 3 if I want. That's still okay. But I think here I'll change this into 5 cubed. Yeah. And then here this will be 6 log 5 25 over 3. And here this will be 3 log 5 25. Now I can bring this 3 down in the front, and here I should change this maybe into 5 squared. And I can bring this 2 down in the front as well. They will cancel, yeah, eventually, yeah. So this will be 6 log 5 5 plus, and this will be 2 log 5 25 minus 6 log 5 20, no, 5, yeah. And you're right, this first one cancels the last one. And what is log 5 25? 2 times 2, 4. That was messy. Now the reason, like I said, there are other ways to do this as well. And you might be thinking, well maybe at the start I should just calculate the value of all of these. I wanted to do it this way because in the exam they could just, if they replaced this 5 here, if they, instead of 5 they said k, then you can't calculate it and you have to use rules here. So I kind of just want practice using the rules. That's why I did it this way. Yep. Okay. Now, last time we looked at a special number called e. Remember? Yeah. So, for example, something like this, log base e, what was it, like 7.29. I think this was 2. I think we said e squared makes 7.29, was it? Something like this? I don't remember. Maybe. Seems believable. What? Well, that's not too bad from memory. 7.38. We said this is about... It's not really too important. We said this is 2, about. Yeah. So just like yesterday, using e is important. So important that when we have something like this, it's given its own special name. We call it the natural log, and we write it as ln of x. So when you don't see a base, the base is actually e. Yeah? Yes? Yes? Now listen carefully. Some people here will make this mistake in the exam. On your calculator, there are 2 buttons. One log and one ll. And they both have no base on it. This here is log base e. This one here is log base 10. We don't use this one. We are using this one mostly. So if I leave out the base, it means the base is E. Okay, so no base written down means use base E. Yeah.
That's confusing because we used to use
Really?
yeah.
Interesting. Here in Ireland and the UK, and I don't know about the US, Ireland and the UK, when you don't write a base on your log, you mean it's base E. You're saying in school for you, no base means base 10. Same for you? Welcome to Ireland. So no base means base E then. Can you calculate log 10? So you all found the ln button on the calculator? Yeah. Okay. The last thing I want to show you is the graph for this function here. Here. Can I go down? Yeah. And in fact, I suppose, you know, you could have a log x. Now, you might be thinking, why don't I have a b on the x, you know, to keep it more general? But we can't really have positive and negative x possibilities, really, because the x should only be positive. So really, what I need to show you is log x graph, because if there was a negative number here, what happens to the graph? Do we know? It just gets turned upside down. So really, is what does the log x graph look like? Does anyone know its shape? I mean, is
like
yeah.
cross the axis. Is that
It does cross the axis though once. The graph goes like this. There's no negative part, so there's nothing here, and it comes from minus infinity and it goes up, and it keeps increasing, but it kind of levels off a bit. Where does it cross the x-axis? In other words, if y is 0, what's the value of x that does this? 1. Log 1 is 0.
It's must past 1.
Must. Here, 1, 0. So this is the graph. So compare that to the exponential we did yesterday. The exponential increases very fast, whereas this graph, it's fast at the beginning, but only at the beginning, and later it changes very slowly. Let me give you a good example. If you calculate ln 1000 and ln 2000, can you give me those values, please? 6.9 and 7.6. Now just think about that for the graph, okay? That means when you're all the way at 1000, you have to move another 1000 only to make a small increase of 6.9 to 7.6. Okay? So what I'm saying is the further you travel, the more you have to travel to start getting increases. Okay?
like
Now,
it seems to be horizontal?
it seems to be horizontal, but it's not. It just will try to become flat, but it's still increasing. But you're right, it seems horizontal. Yeah. Compare that with the exponential. If you calculate even the difference between, 6 and 7, that's going to be a big difference. And the difference between 600 and 605, that's also a big difference. So with the exponential, it changes, it grows very quickly. With the log, it grows very slowly. So in the exam, the shape they want to see, fast at the beginning, but then it looks like it's flattening. But don't go down and don't flatten. Just make it seem like it's trying to flatten. Okay?
Can you describe explain the coursework? Does it?
Ah, yes. No. I'm going to give you an information page I'm going to give it to Donal and he'll give it to you in economics. But if I just to roughly explain the coursework, what's going to happen for the coursework, just really quick, each student, hang on, coursework. What's going to happen is each student is going to get the first 1, 2, 3, 4, 5, yeah. Each student is going to get the first 5 terms in a recursive sequence. Each person will get different numbers. Okay? And what you have to do with the assignment is you have to do things like find the recursive formula. So you need to find a formula here. And then after you find the formula, I want you to complete the table. So make it maybe go to, like U10 or something like this. And then after you find the formula, I ask you to make some graphs. So I want the graph of the sequence. And then I ask you to go on and try and find the formula for un not recursive as a function of n. Like for example, like n squared. Why is this preferred to this? Why do we like this form instead of this form? Why is this better?
This one is like confusing.
Yeah, this one here, you have to calculate each term along the path. Whereas this one here, you can jump to whatever terms. Then once you have this, you need to write it into this form. It turns out it can be written as a geometric. And then once it's been written as a geometric, then I ask you to calculate the sum. So all this work to get to this here, but the advantage of getting to this here is, if I was to ask you to calculate the sum of the 1,000 terms, you don't need to find the 1,000 terms to add them up. Because if you have it written as a geometric and then you can easily calculate this from using the formula. So basically the assignment is in steps. You have data, and the data you write as a recursive, and then the recursive you write as a explicit formula, and then the explicit formula you write as a GP, and then the GP you can use to get the SN.
Is everything handwritten?
No, everything is typed. Yeah.
Do we have to describe
Oh yeah.
graphs?
Yes. So you need to talk about the graph you make and describe it, yeah. So, is it convergent? Is it divergent? Is it periodic? Does it grow quickly? Does it grow slowly? Does it have a limit? Does it not have a limit? Things like this. Yeah. Now, you might be thinking, this is hard and this is difficult and I'm never going to do it. But by the end of it, you'll reflect back on it and think, that wasn't as hard as I thought and it wasn't as difficult as I thought. It might seem difficult at the beginning, but once you start doing it, it won't be as bad as you are probably thinking. Yes, you're thinking, this ain't going to happen for me. But once you get started, it's not so bad.
What's the highest mark that you will get?
The highest mark I gave in intake 1, I think was maybe a 96%. Can you do better? That would be difficult. Because, for example, to go from a 90 to 96 is like double the amount of work. As you move higher, it's more difficult to get higher marks. Yeah. Yes, if you want to do better than 96, go for it. But don't kill yourself trying to do it. Okay. The assignment is worth 10%. So the way I see it, if you can get a 7 out of 10 or an 8 out of 10, or even if you're lucky and you work hard, get a 9 out of 10, that's really good. Okay.
someone gets like 9.6, is
Nope,
10?
stays at 9.6, sorry. Okay, we'll finish there. I'll give you the information page in economics. You don't have to start it now. I think officially the assignment starts after the holidays. I give you 2 weeks, I think. But if you want to use the holiday to get a start on it, that's a good idea.